Hello everyone, welcome to the sixth topology lecture from the Discord Mathematics Discord server. Today we are going to be covering the order topology and then product topology and the subspace topology. So before starting, I will have really recall some definitions like the intervals. So we will need let X be an ordered set. Then also we need the relation less than. Then the intervals are basically just this is called the open interval. This is a set of all x such that x is greater than a and less than b, and there's also the closed interval, which is just the same as the open interval, but we include a and b. And then we also have half open and half closed intervals like this. Okay, so now these are called half open and this is called open. This is open, this is open, this is closed, and these two are half open. Now apparently using this ordered relation we can actually create a topology. So here's the definition of the topology. We call this the ordered topology. So definition, the ordered topology. So first assume suppose X is a set with more than one element. Also X is an ordered set. Okay, so now we basically create a basis. Let B be the collection consisting of all open intervals and then all intervals of the form A0 B, where A0 is the least element of X if it exists. And the third type is the all intervals A to B0. Now we include B0 here, where B0 is the greatest element of X if it exists. Okay, so now this basis, the topology that is generated by this basis, is called the ordered topology. Okay, so that's the definition of the ordered topology. Now let's actually verify that this is actually a basis. So here's our basis verification. First we need to check that every element in X lies in some element of this basis. So first, every X in X lies in some basis element let's say B in this. Okay, so now to show this we can simply just say if x is smallest, for example, suppose if x is smallest, or largest, then it is contained in sets of type 2 or 3, like here. If there is a least element or a greatest element, then in this element x, every element will be contained in some of the dash intervals, in either of these second or third type of intervals. Otherwise, we can just choose a less than x. We can choose such a b, and we can choose such a b such that x will be in the middle of them. X will lie in between, and then just use this open interval, and x is just going to be contained here. So that's the first point, the basis. Now we need to show that the intersection. So we need to show that given b1 b2 in the collection with x in b1 intersect b2, we need another element, we need b3 such that x will be in b3 which will contain in that intersection. So this is very simple. I will just show for this open interval case. So consider intersection of two open intervals, for example AB intersect CD. This is either empty or contains a subset. Let's call it B3, which will be in this intersection. And if we choose x in here, then there will be x. We can choose a subset like this, because the intersection of open intervals will yield another open interval, and that's this basis B3. So B3 is also an open interval if the intersection is not empty. So that's the idea. So we are done with the proof that this is actually a basis, because every element of x lies in some basis element, and it's also closed under the finite intersections, and we can always find another basis elements in those intersections. So yeah, it's a basis. Now let us look at some examples of this order topology. Examples. So the first example 1, this is the standard topology on R. Now R with its usual topology is the order topology, so we can consider this pair R with order relation less than symbol. Then the basis is just the set of all open intervals in R. That's the first example. Now the second example, also let me give an illustration. So it's kind of like you have this real line R, and let's say this is the origin. Now you can choose some open interval. You can choose any open interval. Let's consider this is, for example, n1, n2, and then there's another open interval here. Let's say n3 to n4, and so on and so on. If you take all of these open intervals, eventually you will get R, because also there is a lemma that states that if you take the union of basis elements, then it will equal the topology that it generates. So if you take the union of all open intervals uh, of, let's do n over all positive integers minus n, then this is just going to be equal R. So that's the first example. And now the second example, this is the dictionary order on R times R. R times R. So that's the Cartesian product of R with itself. So firstly we pick 2 points, x1, y1, x2, y2 in this Cartesian product, which I will just write as R2. We define the dictionary order like this: x1, y1 less than x2, y2 if and only if x1 is less than x2, or if x1 equal x2, then y1 less than y2. So it's basically we compare the first coordinates, and then if one is less than the other, then we use that. But if that set fails, let's say x1 is equal to x2, then we will use the second, we will compare the second coordinate. It's like that. So thus this set R2 doesn't have a least element, least or greatest element. So its basis will not fall in either type 1 or type 2 in here. So how do we define the open sets? So we can consider open sets in this order topology are intervals of the form AB times CD. So this actually forms a rectangle with either A less than C and B less than D. So it's kind of like this. You have this rectangle, and this is A to B, and this is C to D. If you consider this rectangle in R2, I call this x-axis and this is the y-axis. This plane is the R2. Then if you consider, for example, if you consider another rectangle here, let's call it E, F and G. Now here I will say, for example, let me draw it a bit better. Let me make it a bit more easier to understand. So intervals of this form. So we have an interval A to B, and then we Cartesian product it with another interval C, D. So this doesn't necessarily have to be there, it can be here. So A less than C, either this is true and A is equal to C. Let me rephrase here. Or A equals C and B is less than D. So this is the case of A less than C, and we can also have, for example, A equals to C. So it's kind of like a rectangle here, like this. It's kind of like a rectangle, and B is also obviously less than D here. So using all rectangles of this form, like actual rectangles, since you saw in that first example that's not rectangle, you can actually generate the topology for R2. So that's the idea for that. Now we can consider the third example. Example 3. This is the positive integers.
Oh my god.
Rokok. Alef? Rokok.
Nah.
Alef? Don't care.
So this is going to, so the set of positive integers z plus has a least element that is 1. So it has a least element that is 1. So it has smallest element, 1. Then the order topology is discrete. Because each singleton that is the set containing a single element is equal to the open interval n minus 1 n plus 1 if n is less than, if n is greater than 1, or the interval 1 to 2 if n, which is the case for n equal 1. So this is the discrete topology because every set we pick is singleton. This is an open set here, so this is open since it belongs to tau, which is just going to be equal z plus and phi, since this is a discrete topology. So now we use basis of this form and this form. We also use this form here as the basis because, as I've shown in the first type 2 basis here for the order topology, this second type here, because there is a least element of the positive integers and that's 1. So now we can also, I think we are finished with these examples. This should be intuitive enough. Now we can look at what we call rays. So first we define them. So definition: open ray. So the open rays are basically intervals of this form, which is the set of all x such that x is greater than a, and then we also have the set of all x such that x is less than a. So it kind of starts like a line and continues on forever, or until the greatest element, let's say b1, if there is one. So apparently if you use these open rays, you can actually, it's not really, it's also an open set, but it's an open set, but the thing is it doesn't really form a basis. It forms a sub-basis. Let me show. So here's our proposition. before that, let us recall what is a subbasis. So recall a subbasis for a topology tau on X is a collection S of subsets of X such that the collection of all finite intersections of X, sections of S, together with the empty set is a basis for tau. So it's basically like if you have a collection of subsets of X and then if that collection S is the collection of all finite intersections of S, if you have a collection of all finite intersections of S and it also has the empty set, then that's a basis for tau. So that's subbasis, I mean. So subbasis is basically a basis without the first condition, it's just the second condition. It's kind of like the analogy if you have studied modern algebra before, then the analogy is like if you have a group and there is also like semi-groups, but semi-group is not really a part of the group, it's basically a group with one less property. It's kind of like that. So our proposition is that the collection of all open rays is a subbasis for the order topology. So the collection of all open rays is a subbasis for the order topology. Now here is our proof. So each open ray is open. This is by definition of order topology. So since each open ray is open, and then if a largest element B0 exists, then the open ray A to this open ray A to positive infinity, the notation is just this form. Otherwise this can be just expressed as the union of all X that is greater than A to X, which just makes sense because these are basis intervals. So since we can express this as a basis intervals, since we can express this as a basis intervals, it's also open. I mean the union, not intersection. Okay. So conversely, every basis intervals every basis intervals is a finite intersection of open rays. Because, for example, if we consider A to be this interval, then this is the intersection of open ray. That is this open ray, we call this the left open ray, intersection with the right open ray. And similarly, for these sets or A, B, 0. So hence topology, the topology generated by the open rays contains the order topology. So here is a proof. So that's, we have shown that this is a subbasis, and subbasis, yeah. Did I mess up the definition of subbasis? Okay. So now I think we are finished with the rays. That was waiting for the order topology section. Now we can do the product topology. Section 15, the product topology. So here's a definition of a product topology. It's basically like you take Cartesian product of two topological spaces. So let x and tau x, y, tau y be topological spaces. The product topology on x times y is the topology whose basis is b equals to u times v, such that u is in tau x and v is in tau y. So that's the product topology, and this is also a basis. Now let's verify basis verification. Let's verify. So firstly, every element of the product is in the basis. So this set itself is in the basis. So that satisfies that every element lies in some basis element. Now we can show the intersection part. So given u1 times v1 and then u2 times v2 in B, if you consider the intersection of u1 times v1 u2 times v2, this is just equal to u1 intersect u2 times v1 intersect v2. This is a set result from set theory, and this is because, and this also belongs to v, since u1 intersect u2 belongs to tau x and v1 intersect v2 belongs to tau y. So now so we have verified that this basis for the product topology is actually a basis. Now we can actually reduce this to smaller bases, reducing to smaller bases. So basically you can actually split these bases for each topological space, and you can actually take the product of those bases, and that's also going to be a basis for this. So here's our lemma that we will need before proving this. Actually, let me state this theorem first. So theorem 15.1, if bx is a basis for tx, I mean tau x, and by is a basis for tau y, then this collection D, which is equal to the product of B times C, where B belongs to Bx and C belongs to By, then this is a basis for the product topology on x times y. So basically you can have two bases, and you can consider the Cartesian products, the collection D, that is the set of all Cartesian products of these basis elements. Then this is also a basis for the product topology. So here's a proof. So let tau be the product topology on x times y, and then let tau prime be the topology generated by D. We show that these two are equal. So first we know for sure that D is contained in B. Also let I should say also let B be the generic basis for tau. Okay, so let tau be the product topology on x times y, and be the basis for tau, and tau prime be the topology generated by D. Now we can see that D is contained in B, because if you consider the basis for B, it has the elements from both Bx, elements from both tau x and tau y. So B has elements from there, and it seems that B is also just the Cartesian product of those elements. So D is contained in B, which implies that tau prime is contained in tau. Okay, so now the next thing is we prove the converse, that we now show that tau is contained in tau prime. So how do we do that? So for any basic element u times v in B, pick P in Px with x contained in P, which is contained in U, and C, which is in By, with y in C, with y in C, which is contained in V. Then this means then this point xy, this belongs to this Cartesian product, agree on this, and then which is also subset of this Cartesian product. So which it means u times v is a union of elements of D. Hence, tau is contained in tau prime and tau equals to tau prime. And then we are done. Also forgive me for always messing up tau and t. I kind of use them interchangeably. I hope that doesn't create any confusions. So that was reducing the basis. Now also in here I said the union of elements of D, which makes sense because D is the set B times C and is the set of all basis elements from both x and y, from both bx and by. So in this argument you can see we picked a basis element from B, which is the topology generated, which is the basis that generates the topology for tau. We picked B in Bx, the basis for the topology tau x, with x with some element x that lies in B and which is contained in U. We picked a basis like that, and since it's a basis, we can do this. We can always pick that point like that, and then we also did the same for y. Then we showed this point lies here, and so this satisfies the definition of a basis. Yeah, so since that's a basis, we can choose points like this, points and that's open sets like this. Also, I have used the lemma 13.2 here, which states that let x tau be topological space, and then there is a C in tau, which is a collection of open sets with the property for every open set U in tau and every point X in U, there exists a C in this collection. Also, let me currently see in this collection such that X is in C, which is contained in U. So it's like if you have this set, this is the open set U also, and then if this property is satisfied, then C is a basis. C is a basis for tau. And let me just read it here. So if you have this open set U and you have this point X, you can have a point C which belongs to this collection. This point C belongs to this collection. This collection C, which is the collection of subsets of tau. So you can using this you can also have another C here. You can have two sets and X could be lying here, and this is just the intersection property of a basis. So I hope that makes sense, and we will not prove it here. We proved it. You can also check the book Moncrief's for the proof. So yeah. So now we can move on to the next important thing, that is called projections. So the definition is we define this function pi1, which maps from x times y to x, and then pi2, which maps from x times y to y. So pi1 xy is equal to x, pi2 xy is equal to y. So these are projections, and it actually can these basically extract the coordinates, the components of the products. So that's how you can think of that. Think of the projections as. And also the inverse image of pi1 under the open set U is precisely the set U times y, and for this inverse image of pi2, this is the set V times x. I mean x times V. Order matters. Okay. And the U and V are open sets. Now this collection, if you take all collections of those two projections, the inverse image of this, then you can actually have a sub basis for the product topology on x times y. So here is the second theorem of this section. The collection S equals to, let me write it here, it's going to get big, inverse image of pi1 of U such that U is open in X, union with pi2, inverse image of pi2 of under V, of V, so the V open in Y. So this collection is a sub basis for the product topology. So here is our proof. So let tau be the product topology. Let tau prime be the product topology, actually be the topology generated by S. Because each element of S is open in tau, we have each element of S is open in tau. We have tau prime contained in tau, which makes sense. Conversely, for U open set of X, V open set of Y open, U times V is equal to pi 1 open set of U under the image of this under pi 1 inverse image of U under pi 1 and the inverse image of V under pi 2. This a finite intersection of elements of X of S hence belongs to tau prime. Thus tau is also contained in tau prime and hence tau prime is equal to tau, and we are done. Now one last thing before we in the product topology section is a counter example. If we consider the product topology, let u1 u2 x and v1 v2 y be open with u1 u2 disjoint and v1 v2 disjoint. Okay. Okay, we don't really need it to be disjoint. So we just let this to be open Now if we consider this is u1 p1, this is u2 p2. Consider the union, call it R, u1 times p1 union u2 times p2. This is open in x times y, but it can be expressed as a single product of the form u times v. So it's basically like you can have rectangles. Union of rectangles is open because it's the union of two basis elements, but it cannot be expressed as a single product. So any product u times v must project to one interval in each factor, but R projects onto u1 union u2 in x and v1 union v2 in y, neither of which is kind of connected, so no single product accounts for R. So also let's look at some examples of product topology. I will show some more examples when we go to the subspace section. So the example is standard Euclidean plane, which is R2. So x equal y equal R. So this product topology with order topology this is a product topology, a collection of all rectangles AB times CD. This forms a basis. So which is the usual topology on R2. Okay guys, I'm back. Now I'm going to be covering the subspace topology. So this is section 16, the subspace topology. Subspace topology. So here's the definition. So this is the definition of a subspace topology. So let X tau be a topological space let X tau be a topological space and we pick a Y which is a subset of X. The subspace topology on Y is tau Y equal Y intersect U for every open set U in tau. So this is called the subspace of X. So let me say y is called the subspace of X. So we have the basic properties here. We have the basic properties. Phi is y intersect phi, y equal y intersect x. So we have the closure and the intersections, and so this means phi and y are in tau y. Then if we consider a finite intersection and have this intersect I, this intersect y, then this is just intersection u. Oh wait, I forgot to put ui here. So it's the intersection of ui and y is the finite intersection. So we have the closure and the finite intersections, and then for arbitrary unions, ui is just equal to, we can distribute the unions over the intersection. So this just, so it satisfies the closure and the ui unions and intersections. So tau y is a topology. So now we can also reduce the basis just like we have reduced it for the product topology. So here's a lemma 16.1. Lemma 16.1, if P is the basis for tau, the basis for tau, then Py, which is just the set intersect y of all b in this basis or basis elements, then this is the basis for the subspace y tau y. So the proof is given x in u intersect y, u open in x, choose p in p so that x is contained in b, it is contained in u. Then x is contained in p intersect y, which is contained in u intersect y. U intersect y. Does that make sense? So we choose x is in a subspace, basically, which is by definition. So it's the element of the topology. And now this just means by lemma 13.2, by is a basis. Okay. Yep. So now lemma 16.2, and now we have another lemma 16.2. Also read the text for more clarity. I'm just sketching things out here. If u is open in Y, and Y itself is open in X, then U is open in X. If U is open in Y and Y is open itself is open in X, then U is open in X. So here's the proof. So say U is Y intersect V for some open set V in X. Since Y and V are both open in X, U is also open. This is by the properties of a topology. Okay. So a subspace is basically like you have this topological space. You have this topological space. Let's say this is the topological space X, tau X, or let me just call it tau, and you can have another subset inside it, which is just Y, tau Y, for example, and this is also a topological space. Basically, you can have a topological space inside another topological space. And what this lemma says that if this set Y is opened, then if you have a set U here, and this is said U is open in Y, then it's also going to be open in X. So that's the idea of a subspace and open sets. Also we also say open in Y. This means that the set is open element of tau Y, or we can also say open relative to Y. That's also said. Okay, so now if we say open in Y, we just mean it's the element of the topology of Y. If we say open in X, then it's in the topology of X. And if open in Y implies open in X, and if Y is open, then open in Y implies open in X as well. Now we can also, before moving on to examples, let's introduce some more stuff that we can work with. Apparently, you can also have products of subspaces. So here's another theorem. This is a theorem because this is important. So 15.3. Let A be a subspace of X and B a subspace of Y. Okay, so let X be a subspace of X. I mean A, not X. Let A be a subspace of X and B be a subspace of Y. Then the product topology on A times B is identical to the subspace topology that A times B inherits from X times Y. So it's basically like if you take the product of two subspaces, it's also a subspace of the product topology. So here is our proof. So now let U times V be a basis element of x times y, where u is open in x, open in x, v open in y. Okay, so now then consider this equation, which is u times v intersect a times b, which should be equal to, by the set theory rules, set theory results, not really rules, you can prove this stuff. Then this is same as saying u intersect a times v intersect b. So this term, this is a basis element meant for subspace topology on a times b. This is a basis element for product topology on a times b, because this is open in a, this is open in y. So the two bases are same, so the two topologies are same, hence the bases are same, the topology is same. This is kind of like this. If you have this space, say x, y, and for example you have this subspace, let's say this is the subspace a times b. This is from you are considering separately. For example, this is the subspace A, this is the subspace B. Consider A times B, so it's like this. Now if you take the product of these two subspaces of X, this will be the same subspace that you find in this product topology. So it should be pretty intuitive to think about. So now let's look at what's the difference between order topology and the subspace topology. So order versus subspace. Subspace topology. So let X be ordered set, order topology, and Y subspace of X, subset of X. Subspace, you can say subspace. Okay, so the first example, consider Y is the closed interval, the subspace of R. Now if you consider the subspace topology has basis elements. This has basis elements A to B intersect Y. And also the order topology also the same basis elements. Now this is the same. This reduces to 4 interval types, that is A, B, 0 to we include 0 to B, since there is a small element, and then A to 1, and then Y itself. So the subspace topology has basis elements of this form, and order topology also has same basis elements, which are these. These two are same, so the order and subspace are same here, are same. Okay, so on this we agree that the order and the subspace topology are the same. But consider this next example, example 2. Example 2, so consider this, consider y equal this set containing 0 and 1 union to subspace of R. Now 2 is open in subspace topology. Since 2 is equal to is same as y intersect open interval 1.9 to 2.1, yeah, since this is equal to that, but this is not open in the not open in the order topology. This is not open in the order topology because every open interval in Y containing 2 must also contain points less than 2, right? Because of the definition of order topology, less than 2. So on this, the order and subspace are not same. So we have the third example here. This is very important. This is called the ordered square. Example 3. Ordered square. is called the ordered square, and this is basically, we pick this interval, we call it I. This is the interval, closed interval from 0 to 1. I times I is called the, actually I times I is a square. Now the dictionary order here, the dictionary order on I times I actually induces a topology, so it's called the, so induces the the ordered square topology, the ordered square topology. And we will denote it by I2 and use this order relation symbol. So now it differs from the subspace topology that I times I inherits from R times R. For example, wait, first let me say I times I also inherits subspace topo from R times R. Now for instance, for example, the vertical segment, this half times half to 1, this is open in subspace, this is open in subspace topology. This is basically we fix the first element, and then, but this is not open in order topology. This figure illustrates it. You fix this line, so this is in the subspace, and it's actually because of convexivity, which we will look into now, and that's the last thing we look into for today, and then some examples and we will be finished. So ordered topology, this product will create some lines like this, but this is not open in the ordered square topology. Okay, so the disagreement comes from subsets that are not convex that are not convex in the ambient order. So let me just define what convexity means, but let me try and explain one last time what is this about. So if you have the order square topology I times I, this inherits the subspace topology from R times R, which basically is a product topology, R times R. There is this product topology which is open in the subspace, but it's not open in the order topology, because order topology, if you remember, it consists of the rectangles that you compare using the order. So yeah, now let's look at, and these lines are not really unions of, this cannot be, these are not unions of the rectangles. Actually, forget what I said. I think I'm missing things out, but okay. So let's move on to convexivity. About that, let's move on to convexivity. So convex sets, convex. Okay, wait. I think it's not the product topology, it's the dictionary topology. My bad. So the dictionary. So R times R with dictionary topo. So this has dictionary. So the subspace property of I times I versus I times I having its own dictionary order is actually different. Okay, yeah. Yeah, we don't have intervals here that we can compare, so this is not open because you cannot describe this as the union of the intervals. So now let's move on to convex subset. So definition. This is according to Moncrief's book. So let X be an ordered set. A subset Y of X is convex in X if A be in Y and there is some X between A and B, if this implies X is in Y. So equivalently you can say Y contains every open interval determined by its own points, and intervals and rays of X are therefore convex. So apparently if you have an ordered set in the ordered topology and the subset of X that is convex in X, then the ordered topology is the same as the subspace of X. So up here we had these two examples. In here the subsets, they were actually convex. The subset here was actually convex in this first example. So that's the reason why this theorem makes sense. So now theorem 16.4. This is the last theorem for today. Let X be an ordered set. Let X be an ordered set in the ordered topology. And then let Y subset of X be convex in X. Then the ordered topology on Y is the same as uh, topology, subspace topology. Subspace topology, y inherits from x. So here is our proof. Consider the ray consider this ray in x. What is the intersection of this with y? So if A is in y, then if you take intersection of this ray with y, we simply take all x that is greater than a that's present in y. So this is an open ray of the order set y. This is an open ray of the. Now, if A is not in y, then A is either a lower bound or an upper bound on y, since y is convex. If it's a lower bound, if A is a lower bound, A to positive this ray intersect y is equal to y. If upper bound, then this intersection is empty. So the intersection of this left ray with y is either open ray of y or y itself, or otherwise empty. Since this ray intersects y and this ray intersects y from a subbasis, for subspace topology on x, y, on y, and it is open in the order topology. The order topology contains the subspace topology. Contains the subspace topology. So to prove the reverse of this, open ray, any open ray of y equals the intersection of an open ray of x with y. Therefore, it is open in the subspace topology on Y. Since the open rays of Y are subbases for the subspace topology on Y, since the open rays of Y are subbases for the order topology on Y, this topology is contained in subspace topology. And then we are done. Okay, that was a big proof. So now the last thing we will do now is look at some examples of subspaces and product topologies. So more examples. The first example is very famous. It's called a torus. So S1 is called the unit circle, which is defined as set of all points x, y in R2 such that x square plus y square is equal to 1. Now if we take the product S1 times S1 is called 2 torus. It's like the topological surface of a donut. Basis elements, first let me draw this. It's like this. So basis elements are arcs of one circle times arcs of other. So multiplying two circles actually give you this torus. So that's an example of a product topology. So now the next example we have is called an open annulus. Also this is subspace of R2 as I said. So now let's look at the open annulus. Now consider S1, consider S1 and S1 times R1 R2, which is a subspace of R with R1 and R2 positive and R2 is less than R1. This product is an open circular band around the radius r1 and r2 in r3. So this is a subspace of r3 now. Okay, so it's like this. It's two circles. It's like a band. So this is r1 and this is r2. And basis elements are arcs of S1 times open radial subintervals. Also, just S1 is also called the one-dimensional circle. It's like this in the plane. And then we also have the S2, which is also called the two sphere. This is called the one sphere. Then there's S2, which is called the two sphere, and S3 is three sphere, and so on. Now these are some cool examples. Now we can also create a cylinder. So if you take S1 times this closed interval 0 to 1, this has surface topology of a cylindrical shell. It's like this. So yeah, that's it. So that's the end of the lecture. Thanks for being till the end. If you have any questions, feel free to join the Discord server, and that is discord.gg/maths. We have this S here, so feel free to join the Discord server and ask me questions. Thanks for your time. Bye.